Welcome to lecture number 48 of fuzzy sets, logic and systems and applications. In this lecture, we are going to discuss fuzzy rules and fuzzy reasoning. So, in this lecture, we are going to first take up the fuzzy if-then rule. So, let me, before going ahead, tell you that fuzzy if-then rule is an essential component of a fuzzy system. So without fuzzy if and then rules, there is no fuzzy system. So this means that in any fuzzy system, we must have a set of fuzzy if-then rules. A fuzzy if-then rule is also known as fuzzy rule, fuzzy implication, or fuzzy conditional statement. So fuzzy if and then rule has a form of if X is A, then Y is B. So this is the syntax of any fuzzy if and then rules. So here we have two components. First component of this fuzzy if then rule is the antecedent or premise. So this part is called the antecedent or premise. And then the second part, which is just after then, is called the consequence or conclusion. So in any fuzzy if then rule, will have a antecedent part or premise part and consequent part or conclusion part. And it is very important here to note that antecedent part in fuzzy if and then rule is always fuzzy. This means that A is always fuzzy. A is a linguistic value and which is always a fuzzy quantity, a fuzzy set. Whereas we have the consequent part or conclusion part, and this consequent and or conclusion part has B, and this B can be either a fuzzy set or a crisp value. And this crisp value can be expressed in terms of some function which is actually the function of the generic variable. So we can say that the A that has been taken here in this fuzzy rule, fuzzy if-then rule, A is a linguistic value. A is a linguistic value characterized by a fuzzy set with the universe of discourse capital X, and B here can be either a linguistic value, and of course we all know that a linguistic value can always be represented by a fuzzy set. So A is a linguistic value. A is a linguistic value characterized by a fuzzy set. Whereas B can be either a linguistic value, that means a fuzzy set, or a crisp value expressed in terms of a function of linguistic variables used in this. For example, here the linguistic variable is X. So this is the linguistic variable. Alright, so now often X is A is called antecedent or premise, as I have already mentioned here, while Y is B is called the consequence or the conclusion. So this must be understood very clearly, and as I have already mentioned, the fuzzy if and then rule is very important component of any fuzzy system, and without a set of fuzzy if and then rule, the fuzzy system cannot exist. So let us now move ahead and we discuss a fuzzy if then rule where we have, let's say, the fuzzy if and then rule like this, like if X is A, then Y is B. So let us first understand that this can also be represented by A entails B or A coupled with B. So please understand here, as it is written here, that there are two ways to interpret a fuzzy if then rule. First way is A coupled with B, or the other way, the second way is A entails B. So fuzzy if then rule, when it is written in that syntax that I have already mentioned, like if A is A, X is A, then Y is B. So this can also be interpreted like this, like A coupled with B, or A entails B. So assuming A and B both are fuzzy sets. So let us please understand, let us assume here that A and B both are the fuzzy sets. So when we assume A and B, means for A and B, both fuzzy sets. Alright, so please understand, why are we saying this, that for A and B both fuzzy set? Because B can be here in fuzzy if and then rule, B can be either crisp or fuzzy. But here we are assuming for this discussion that we have both A and B fuzzy sets. So assuming A and B both fuzzy sets, if and then rule can be defined as a fuzzy relation. So this is very important to note when we have A and B both fuzzy sets. So in this case, this A entails B, A coupled with B can be regarded as a relation, and this is represented by R. On space X cross Y, where this X is the universe of discourse for the generic variable small x, and Y is the universe of discourse for generic variable small y, if B is the fuzzy set. So this needs to be noted. So when we have a relation, when we have a fuzzy relation in between capital A and B, we can always write this as A cross B. We have already done this. So R is equal to A entails B is equal to A cross B. You can see here. So this way we can write that for continuous fuzzy set, this is for the continuous fuzzy set, that we have the integral sign x cross y, that means the space, the universe of discourse becomes capital X cross capital Y, mu r x comma y oblique x comma y for every xy belonging into capital X cross y. And similarly for discrete here, we have the representation as capital R, A entails B is equal to A cross B is equal to the summation X cross Y mu R X comma Y oblique X comma Y for every X comma Y belonging into capital X cross Y as the universe of discourse. So what we have seen here is that if we have in fuzzy if and then rule, both A and B, A is coming from the antecedent part or premise part, and Y and B is coming from the consequence or conclusion part. So if we have A and B, both fuzzy sets that are coming from fuzzy rule, if and then fuzzy rule, then we can write the R relation fuzzy set in terms of A and B. That means A cross B, and A cross B for continuous we have seen here, and for discrete we have seen here as to how we can write. We have already discussed in detail fuzzy relations, so we can accordingly manage to write the fuzzy relation matrix. So if A entails B is interpreted as or A coupled with B, so both are same. So A entails B, A and then arrow, forward arrow, B is interpreted as A coupled with B. Then it can be interpreted by a fuzzy relation R, as we have just discussed. So for continuous, the relation can be written as, R can be written as here, A coupled with B is equal to A cross B, means the Cartesian product, simple Cartesian product, as we have already discussed in previous lectures. So here the mu of xy, how will we find this? Mu of xy is here. So this mu of xy, you see here, mu of xy, this mu of xy we can get by suitably taking the Cartesian product, means we can get by using the T norm. So here this is nothing but, this gives us mu of R x y. So this we can get by taking the T norm of A and B, means we take the T norm of mu A of x and mu B of y. So as we have already done this T norm in previous lectures, so the fuzzy relation R and T. Let's say we have two fuzzy relation sets, right? And then accordingly we can have the T norm operators we can apply, and then we can say that there are four different fuzzy relations which are defined using four commonly used T norm operators. What does this mean? This means that we have in T norm we have multiple T norm operators. So we have four commonly used T norm operators. First is A coupled B using minimum T norm operator, and then the second is the A coupled B is using algebraic product T norm operator. Then we have the third one is A coupled B using bounded product T norm operator. And then we have the A coupled B using drastic sum product operator. So this way we can use any of these T norm operators suitably to get the mu r x y. And this was for the continuous. On the same lines we can get the r for discrete. The relation matrix, the relation in between A and B for discrete fuzzy sets. So let us now go one by one. So fuzzy rule interpretation as A coupled B here, and this A and B are coming from the if and then fuzzy rule. So let us take the first case where we have the minimum T norm operator. So we have, let us first type of T norm operator. So first type of T norm operator is min. So for continuous fuzzy sets A and B, where this R is the relation fuzzy set which is coming out from A cross B. So the Cartesian product of A and B. So we write here the relation, fuzzy relation set as R min, because min is here denoting that the minimum T norm operator that is being used for getting the fuzzy relation in between A and B. So this can be represented by this. And similarly, when A and B are discrete fuzzy sets, then this R min can be written as this. So here we have the fuzzy relation set when we use min. So we can write min T norm, and then for discrete here we have when we have A and B both are discrete. So this way we can represent the fuzzy relation matrix, fuzzy relation set. And when we have, instead of min as the T norm, the algebraic product T norm. So when we have algebraic product T norm operator, then we simply, instead of taking mean, we take the product in between mu A and mu B. You can see here. So we take the product here. So mu A of x cross mu B of y. So we take the product in case of algebraic product T norm operator. So, and we write this as RAP. You can see here. And similarly for discrete RAP. So for discrete A and B, for discrete fuzzy sets A and B, we write the relation fuzzy set by RAP, which is nothing but A cross B summation x cross y as the universe of discourse, and then here again we have the product. Here again we have the product in between mu a of x and mu b of y, and then rest of the things remain the same. So only difference here is that this operator here, this operator gets changed. So when we have min, we simply take the min. When we use min t-norm, we take the min sign here, and inverted. When we take min, it means we take the minimum of mu a of x and mu b of y, and when we use product, then simply we multiply. Similarly, when we take the bounded product t-norm, so we use this formula. We have already done this when we have discussed the all t-norm operators. So here we have bounded product. So for bounded product, in between bounded product of mu a of x and mu b of y, we write 0, and then the max sign of means the max in between 0 and mu a of x plus mu b of y minus 1. Similarly, when we have discrete fuzzy set, we write it this way. So let us understand now that as to how the various t-norm operators change the computations. So you see here the fourth one is A coupled B using drastic t-norm operator. So here when we have drastic operators, we use for drastic computation, for drastic product computation, this function. So when we use this for mu a of x and mu b of y, we can write it like this: mu r dp of x comma y, and this mu r dp x comma y can be computed by the drastic product t norm. So this way we have seen that as to how we can manage to get the fuzzy relation set by using all the 4 types of t-norm operators. And if we have here an example, we take an example here where we have a high speed S, which is characterized by a fuzzy set. So S high is the fuzzy set with the universe of discourse S 20, 25, 30, 45, 50. And we have another fuzzy set here, P high, and with the universe of discourse 1, 2, 3, 4. So we have two discrete fuzzy sets. So both, I can write here, both the fuzzy sets are the discrete fuzzy sets. So S high and P high both are discrete fuzzy sets, where S, P both represent the speed and brake pressure respectively. So determine the implication relation, that means the relation fuzzy set for this. So S high, and then here S high coupled with P high using the interpretation, the same interpretation that we have just discussed. So let us quickly use all 4 operators, 4 t-norm operators, and let's see how we are getting various relation fuzzy sets. So we have 4 t-norm operators. So for the first t-norm operator, that is the min t-norm operator, we can quickly find the R min, the relation fuzzy set, the relation fuzzy set R, And since we are using min t-norm operator, so we use the min here. See that here we use min operator as the t-norm. So we have already done this exercise in previous lecture. So when we do that, we are going to get this as the fuzzy relation matrix. So this is fuzzy relation matrix or min. Similarly, when we use the algebraic t-norm operator here, so then now the computation becomes a little bit different. So instead of taking min of the membership values, we multiply the respective membership values. You can see here. So like 0.2 multiplied by 0.4. So this is the case when we have the algebraic product. So we simply take the product of the membership values. So this fuzzy relation matrix RAP. So please understand that this RAP is a fuzzy relation set which is represented in the matrix form. So RAP is a fuzzy relation set. So fuzzy relation set RAP, which is represented in the form of a matrix. So when we take the multiplication, when we do the multiplication in between the respective membership values, so now what we are getting is this. So this is nothing but the fuzzy relation matrix RAP when we have used the algebraic product t-norm. Similarly, let us now take the third type of t-norm operator. So when we take the bounded product t-norm, let's see what happens. So when we take bounded product t-norm, so we use this formula, this relation, this expression for finding the bounded product t-norm, and this is nothing but we take the max in between 0 and the mu s high of s plus mu p high of p minus 1. So this way, when we apply this to all the pair of membership values, here you can see all these values, and please note that when we are finding the relation in between A and B discrete fuzzy set here, and since we are taking the A cross B for getting the relation fuzzy set RBP, or maybe whatever type of t-norm we apply, but A and B must be multipliable. So this means the order of A and B should be in such a way that they can be multiplied. So these two matrices can be multiplied. So whatever we are getting after this is here. So when we use the bounded product t-norm, the relation, the fuzzy relation matrix is, if I write it by RBP, so this is fuzzy relation matrix, and this comes out when we use A and B discrete fuzzy sets, and we use the bounded product t-norm operator. So now let us take the fourth kind of T-norm operator, that is drastic product T-norm operator. And we all know that when we use drastic product T-norm operator, this expression applies. This means that if mu p high of p is 1, then mu r dp of sp is equal to mu s high s. And then if we have mu s high s is equal to 1, then mu p, then mu r dp of s comma p will be mu p high of p. Otherwise, the mu r dps comma p will be 0. So when we do that, when we apply this condition, then the RDP, which is here, which is the fuzzy relation matrix based on the drastic product T-norm operator, we get here RDP. So this way we have seen that as to how we can get the fuzzy relation matrix by using various kinds of T-norms, all four kinds of T-norms that we have used in previous lectures. So the first was the minimum T-norm operator, and then the second one was the algebraic product T-norm operator. The third one was the bounded product T-norm operator, and the fourth one was the drastic product T-norm operator. So all these four types of T-norm operators we have already studied, and we are applying this here to get the relation built by using all these four kinds of operators, T-norm operators. So with this, I would like to stop here. In the next lecture, we will continue with the fuzzy rules and fuzzy reasoning. Thank you.